All right, let's dive straight into this OCAP board review explainer where we're going to build true clinical mastery of angular magnification, leaving all that rote memorization behind. Look, I know basic optics can sometimes feel like this dry, endless list of formulas, but today we're going to look at this strictly through the lens of a clinician. We're connecting the raw physics to the actual anatomy and physiology of the eye so you understand exactly what's happening when you hand a low vision patient a magnifier or even when you're just looking through your surgical loupes. We are going to build a mental model so incredibly strong that you won't just memorize these board formulas, you'll deeply understand exactly why they absolutely have to be true. Here's our roadmap for today. First, the limits of transverse magnification. Second, introducing angular magnification. Third, the optics of simple magnifiers. Fourth, the standard reference distance. And finally, number 5, calculating that high-yield board math. Okay, part 1, the limits of transverse magnification. Let's start things off with a classic board trap. Seriously, they love this one. What is the transverse magnification of a telescope? I actually want you to pause for a second and think about this. If transverse magnification is image distance over object distance, what exactly happens with an afocal system looking at a distant star? What's your immediate gut reflex here? The answer? It's mathematically 1.0, meaning, on paper, there is supposedly absolutely no transverse magnification at all. Now, intuitively, that feels completely wrong, right? I mean, what good is a telescope if it doesn't magnify? But we have to look strictly at the math of transverse magnification, which is simply the image distance divided by the object distance. So why does it break down? Well, because focus rays aren't involved in these afocal systems, transverse magnification breaks down entirely. It basically just approaches 0 or infinity. Remember, a telescope is an afocal system. You've got parallel rays from an object way out at infinity entering the lenses and parallel rays exiting to form an image at infinity. If both your object and your image are at infinity, your formula is infinity divided by infinity. Mathematically, that equates to 1.0. The formula basically just self-destructs. And this brilliantly illustrates our core mental model for today. Transverse magnification simply cannot meet all our needs, so we absolutely must shift over to angular magnification, which measures the apparent size on the retina. Transverse magnification tells you how big things actually are in physical space. But let's be real, as ophthalmologists, what do we care about? We care about the retina. We care about how big things look to our patient. Grasping this is a massive paradigm shift for your clinical thinking. Moving right along to part 2, introducing angular magnification. Remember, from your basic ray tracing back in the day, the nodal point of the eye is the absolute boss when it comes to where an image lands on the retina. The nodal ray is that undeviated ray that passes straight through the optical center of the eye and strikes the macula. The angle that the specific ray creates is called theta. This right here is the physiological basis of vision. It's the actual physical footprint that light takes up on your patient's photoreceptors. So the crucial takeaway here is that just by bringing an object closer to the eye, the angle subtended on the retina gets larger. It makes the object look bigger to the patient, even though its physical transverse size is literally exactly the same. Think about it. Hold your thumb out at arm's length and then bring it an inch away from your eye. Your thumb didn't physically grow, right? Its transverse size is identical, but the angle it subtends on your retina, its angular size, just massively increased. All right, part 3. The optics of simple magnifiers. Let's walk through how this builds sequentially, step by step. Picture an 85-year-old patient sitting in your chair with severe atrophic macular degeneration. By placing the reading text exactly at the primary focal plane of a plus lens, the light rays exit that lens completely parallel. When those parallel rays enter the patient's eye, the nodal ray passes through at a much steeper angle than it would have without the lens. That steeper angle creates a massive footprint on the retina, which the patient's brain then interprets as a giant virtual image sitting way out at infinity. Therefore, a bump in the dioptric power of that plus lens directly increases the angular size of the image hitting the retina. We denote this new magnified angle as theta prime. If you hand your patient a higher power lens, the rays are bent even more steeply, the nodal ray angle increases, and boom, the image on the retina gets even bigger. But remember, magnification's a relative concept. That means we have to compare this new, larger angular size to a baseline unmagnified angular size. Guys, this is a super common board trap. Magnification isn't just asking how big is it now. It's a ratio. It's asking how much bigger is it now compared to how big it used to be. We take our new magnified angle, theta prime, and we divide it by our baseline unmagnified angle, theta.
Which brings us perfectly to Part 4, the standard reference distance.
Time for a little active recall. Pause again and think about this. If angular size changes depending on how close you hold the object, what standardized baseline distance do we strictly use for our denominator? Seriously, think about it for a second. If magnification is relative and a patient can just pull a book closer to their face to make the unmagnified angle larger, how do we establish a universal medical standard for what 1x magnification actually is? Write this down. Seriously. Engrave this absolute OCAB pearl into your brain. The arbitrary reference distance used to calculate standard unmagnified retinal angular size is exactly 25 centimeters or 0.25 meters. This number wasn't just chosen out of thin air. Historically, 25 centimeters is considered the standard near working distance for an average adult reading a book. By establishing this absolute constant, we freeze our denominator. Now, every single time we calculate magnification, we are comparing the lens magnified view to what the naked eye would see at exactly 25 centimeters.
All right, home stretch, Part 5, calculating the high-yield board math.
Now, check out how beautifully this math works out. When we set up our ratio, it elegantly cancels out the object size entirely, leaving us with just lens power multiplied by 0.25. Let's trace the logic real quick. Our magnified angle is object size times lens power. Our baseline unmagnified angle is object size divided by our standard reference distance of 0.25 meters. When we divide theta prime by theta, the object size is sitting on both the top and the bottom of the fraction. They completely cancel each other out. This is incredible because it means the magnification power of a lens is an inherent property of the lens itself. It literally doesn't matter if the patient is looking at a tiny pill bottle or a giant newspaper headline. A 5x magnifier is always a 5x magnifier. And since multiplying by 0.25 is exactly the same as dividing by 4, that brings us to the ultimate high-yield formula for simple magnifiers, lens power divided by 4. This right here is the absolute money formula for your exams. If you have a 20 diopter lens, you simply divide 20 by 4 and you instantly know it's a 5x magnifier. If a board question tells you a patient is using a 10x simple magnifier, you just multiply by 4 and instantly know they are looking through a 40 diopter lens. This formula is lightning fast, it's totally reliable, and now you understand exactly the optical physiology of why it actually works. All right, let's do a rapid-fire review of our top board pearls before we wrap up. Telescopes have a transverse mag of 1.0. Transverse is actual size, while angular is apparent size. Always use 25 centimeters for your baseline reference. And finally, calculate angular mag by dividing lens power by 4. If you internalize these 4 core pearls, you are going to easily collect points on test day. Do not confuse transverse with angular. Remember your infinity over infinity trap, and lock that 25 centimeter, 0.25 meter reference distance into your memory banks for good. To truly cement this clinical mastery, I want you to consider this final provocative thought for your next clinic day. Because understanding the why behind these optics is what separates rote memorization from outstanding patient care. Think about it. If a patient walks in with a 5x magnifier, you now know instantly that's a 20 diopter lens. But far more importantly, you understand that those 20 diopters are aggressively bending parallel light to strike the nodal point of their eye at a much steeper angle. It's casting a dramatically larger footprint over whatever remaining healthy photoreceptors they have left. You aren't just doing math, you are maximizing the biological capacity of their macula. Keep that perspective with you on the wards, and I will see you in the next explainer.